Howdy everyone, this is Mr. Palmer with Bowtie Physics. Today, I want to review Newton's first and second laws and introduce you to free body diagrams. Free body diagrams are an integral way to visualize the forces acting on an object. The object is simply drawn as a box. You don't have to be an artist here, with arrows representing the forces acting on it. Note that each arrow begins in the center of the box and points in the direction of the force acting. Even if the object is pushed from the left, the arrow needs to start from the center and move out towards the right, in the direction of the force. We'll practice drawing free body diagrams in this flipped lesson and during our next class. Free body diagrams serve as a great companion tool to connect concepts from our previous kinematics unit to Newton's laws in our current unit. For example, when analyzing a briefcase that rests on a tabletop, we know that Newton's first law states, an object in motion stays in motion, and an object at rest stays at rest, unless acted upon by an outside net force. It is important to note the language regarding a net force in Newton's first and second laws. It does not state that since the briefcase is at rest on the tabletop and continues to stay at rest, that there are no forces acting on the briefcase. In fact, there is never a situation where zero forces act on an object. Redrawing our briefcase on the tabletop, there is always the force of gravity pulling downwards on every object. So why isn't the briefcase accelerating downward due to gravity, like an object in freefall? Because there is an upward force applied by the table. So there are actually two forces acting on the briefcase. But since the force of gravity acts downward, and this force acts upward with equal magnitude, they cancel out and result in zero net force, confirming Newton's first law that an object at rest will stay at rest since there is zero net force acting upon it. Now this force is called the normal force, Fn. A normal force is applied by a surface, whose direction is always perpendicular to the surface. In math and physics, normal means perpendicular, so a horizontal surface will always apply a vertical normal force, and a vertical surface will always apply a horizontal normal force. The normal force is always perpendicular to the surface. Many of the objects around us in the real world come into contact with surfaces, so it's important we understand the normal force so that we can draw the free body diagrams and analyze the forces acting upon them. So let's revisit the briefcase at rest on the tabletop. We can apply Newton's first law because the briefcase is at rest and stays at rest, since the force of gravity and the normal force cancel out, causing the net force to equal zero. The free body diagram, or FBD, helps us see that the net force is zero because it visually shows that the forces acting on the briefcase are balanced, which indicates that we can apply Newton's first law. But what if the forces acting on the briefcase weren't balanced, with a force pushing it to the right across a frictionless surface? This force, acting on the mass of the briefcase, would result in acceleration, which is Newton's second law. We commonly rewrite this in linear form, that F equals ma, keeping in mind that we're discussing the net force. The free body diagram helps us visually see that this net force is causing an acceleration because it is unbalanced to the right in the direction of the push and in the direction of the acceleration. It is important to note that the net force is not an actual force acting on the briefcase, but a result from adding up the forces on the free body diagram. The gravity acting downward and the normal force acting upwards cancel out, so that the net force is actually the force of the push to the right. But what if the situation's not so simple? What if the tabletop that the briefcase is being pushed across wasn't frictionless? The force of friction resists motion, therefore acting to the left and changing the net force acting on the briefcase. Applying Newton's second law, we can determine the net force by using the free body diagram such that the force of the push minus the force of friction equals the net force, which results in the acceleration of the briefcase. Since there's only a little bit of friction, that free body diagram is still unbalanced. But what if that friction force was stronger and was able to actually match our push, such that the free body diagram with gravity, the normal force, our push, and the new friction force is now balanced. This free body diagram is balanced, meaning that the net force acting on the briefcase is 0, so that we can apply Newton's first law to the briefcase sliding across the tabletop. An object in motion stays in motion unless acted upon by an outside net force. In this case, the briefcase would be sliding with constant velocity. Okay, so let's review. Newton's first law can be applied when the forces acting on an object are balanced, as can be seen in these free body diagrams. In this case, the net force is 0, and the acceleration of the object is also 0. That means that it moves with constant velocity. This means that the object could be at rest, being pushed across the surface at constant velocity, or moving across a frictionless surface at constant velocity, like a hockey puck sliding across the ice. Newton's second law applies to situations where the forces are unbalanced, resulting in a net force that causes the object to accelerate. This can be seen in the following free body diagrams, where an object is pushed across a frictionless surface, or when the applied force is great enough to overcome the force of friction, creating a net force that causes the object to accelerate. Another example is an elevator accelerating upwards due to the unbalanced force of tension overcoming the force of gravity. I hope this has been a helpful review for free body diagrams, and I look forward to seeing your work in class tomorrow. Signing off.